Hello everyone, we're Team 12 and today we'll be demonstrating our implementation of synchronization and consistency in our system. First, let me show our 5 replica server setup. We have 5 servers running simultaneously, each running on different devices. If the leader server fails, clients can switch to another replica using our leader election algorithm that we discussed in our previous demo. So I have the first server running on my device on port 3000.
And I have the second server running on port 3001.
I have third server here, so that's index 2.
I have the fourth server running, and that's on 3003.
I have a fourth server running here. It's port 3004.
Okay, so I'll be explaining about how different features use our process queue and about the process queue function. So, as we know, in a turn-based game like Uno, the gameplay naturally follows a clear step-by-step order where one player goes in the next. And because of this, we don't really need the complex systems used in environments where many things happen at once, like parallel RAM or memory coherence protocols. Um, so as for the sequential nature of Uno, by design, it's a turn-based game. So each move happens one at a time in a fixed order. That just means that there's no need for multiple players to access or update the game state at the same time. This built-in order ensures that everything happens in a predictable way, and there's no need for parallel RAM or coherence protocols. And in systems where a lot of things happens at once, we need things like parallel RAM and a memory coherence to keep everything consistent and avoid any errors. But since Uno is sequential, we don't really face those issues. The game state updates one moves at a time, so we can avoid that extra complexity. And by using process queues for sequential consistency instead of parallel memory setups, our system uses process queues. So these queues keeps actions in orders, and each player's move is added to the queue and handled in the correct turn order, keeping the game state more consistent. And we can see in this function. And um, since moves are also processed one by one, the game state stays accurate and up to date. It just keeps things simple by only dealing with one move at a time, and we don't have to worry about the challenges of synchronizing parallel operations. It just makes our system more cleaner and easier to manage. In summary, because Uno is a turn-based game, we need the complexities of parallel RAM and memory coherence. If a system is sequentially consistent, it also meets the PRAM and coherent requirements as well.
As my teammate mentioned earlier, we are using our system is sequentially consistent and uses both PRM and coherence. Now we're going to talk about synchronization. In our game, we have 3 types of synchronization. First, we have a turn-based logic. Because like a deck and a top card pile will be shared across all users, they are all critical sections of our application. So we have the way we kind of try to remediate any race conditions was to create a turn-based logic. So every update is done by one player at one time. And second, we have to synchronize the same deck and top card across all players, meaning each player has to have the same deck as the other players and the same top card as the other players. And third, we have to synchronize the data of a game across all servers between readers and replicas. I'll be going through the first one, which is our turn-based logic, to prevent risk conditions. So we have a game running right now. So I'll just do one move here. And now let me try to do another move like drawing. I can't do the drawing because I only have one move, and now it's for the other player to do a move, and then I'll be able to do a move again. Um can you do a move, Samara? Okay, now she made a move. Now I can actually make another move and it will actually work. If I do it again, it won't actually work. Now I'll talk about the second synchronization where all players will have the same deck. Right now on the draw pile, which is the deck, we have green 6 as the next card. I'll ask my teammate to draw one card now. As you can see, like the card went away and now it's red free. I'm gonna draw the card now and it's actually red free. Now I'll pass it to Samara who will talk about the global state.
For maintaining consistent state across all replicas, we've implemented the Chandy-Lamport snapshot algorithm. The leader server captures the game state after every critical game action, for example, drawing a card. And then it broadcasts to all replicas using the broadcast snapshot to replicas function. This function gets the current game state using the capture snapshot state function, and then it sends it to all the replica servers we have. This ensures that every server has a consistent view of the game. Now I'll perform an action on the client, like drawing a card. So as we can see in the server logs that the leader server captured the snapshot, and it should broadcast it to all the other replicas. Nadia, can you share your screen? So as we can see, the replica received the snapshot as well, and it updates their local set accordingly. So this concludes our presentation. Thank you.